patent for it or the copyrights, and at the end I wrote the paper with them, publish it in repetitive journal.
Okay. And you said, how many students did you have previously?
Three.
Three? Okay.
Per year I sent 3, but not only working with me, this time we send like 9 students.
Okay.
And then we separate, it depends
Amongst
on,
like
yeah,
disciplines.
yeah,
Okay.
yeah.
Okay.
It depends on what kind of things that they are.
And these are all engineering students?
Yeah.
Okay.
Engineering mostly for IT, computer science, and then computer engineering.
Okay.
But they can working in any, one student working with the finance department, but they are making AI for finance.
Okay.
Something like that.
All right. Got it.
The director of our EPICS program. So obviously we're a little bit full with lots of people, so we'll figure out how the evening goes. We got a smaller room because there's a big conference going on. But very simply, we will have 8 teams tonight pitching for funding to start a venture. So for a lot of you that are here for the skill session credit or to support your friends, the goal of today is to think about how they will grow and scale their project into a venture or a company.
Surgeries to prevent lung failure or heart failure. So within Arizona, there are only 27 of these machines, and they're all localized in very heavy populated areas, as you can see in this map.
For Canadian sign language content is also available, and students fall behind due to the lack of English skills.
So, our solution, the offline digital library. We were told that all these students...
As the territorial normal school, that was the school's name in 1885. So it is a bit of an older school, not as old as some of the other U.S. institutions like Harvard and MIT and NYU. They're pretty old as well, but we're maybe a little bit newer to the game. So we've gone through a few different name iterations. At one point, we were specifically a teacher's college. That was the point of this state school. You have Arizona State University, and then you also have the University of Arizona, which is further down south in Tucson. They're about an hour and a half from here. So ASU at the time was considered to be a teacher's training college. In 1958, our name was changed to Arizona State University. We've gone through a couple of iterations of mascots, but we are officially the Sun Devils. So that is Sparky, our mascot. Research University, and we are measured, and we'll measure our activities by whom we campus over the next couple of days, but or at least you'll see signs for. But some of these researchers are still active. These centers are still active. We have new centers. Some of these have gone away, but we're a very, very large, like I mentioned, workforce development and faculty development. And so here's an overview of that Center of Excellence. So with the cross-cutting themes on the left, the centers of excellence that we'll focus on are semiconductors and advanced packaging, microelectronics and embedded systems, and then AI integrated smart manufacturing. And then over to the right, we've got examples of all of the activities. So some that I think you may find specifically interesting, like our K through 12 outreach. So like our STEM, developing our STEM pipeline and activities, upskilling and reskilling. We'll have degree programs, industry-sponsored research. There will be an annual symposium, innovation and entrepreneurship boot camps with the students, as well as startup incubators and accelerators. So that's what we're looking to achieve as outcomes and activities from the Center of Excellence. So this campus is home to some of our teachers college programs, as well as our engineering programs, so like aviation, robotics, autonomous vehicles. So for the engineering schools, we have the Polytechnic School, and then we have the School of Manufacturing Systems and Networks. They're both out.
Robots, that's not what industry uses, right?
Yeah.
They want larger robots, more industrial relevant software and hardware. Now, of course, we can never be close to what industry uses, but they said as long as you have some level of control. Right, so this is we don't have a fully clean room, we have a class 10,000 clean room. We have other clean rooms on other parts of the campus. Are they visiting microtechnology works?
They are
They are.
tomorrow.
Oh, tomorrow. Okay, so you will see bigger fabs. But what we want to use this is for teaching. Have students wear the bunny suit and work with equipment for 4 or 5 hours, because that's what companies, they want them to work in that setting. I know, of course, Dory has a lot of work in the area. But that's what we want to replicate here. Trying to work with AMCOR, TSMC, Intel to run this program. Here what we do, yeah, please take pictures, video. Autonomous blimp, autonomous drones, autonomous ground vehicles is what we want. We will have a net in that corner of the RAM. It's high ceiling so they can fly a drone as long as they don't hit the top part. There's autonomous blimp is what we have a student competition that they go for that. We'll have that set up all here. Yeah, I told you about AI and one of the things that, when we learn as a 1-year-old or a 2-year-old, 3-year-old, if I say, take the red block and put it in the box, very easy for us to do it, right? Question now is, can an AI, if you use ChatGPT, can an AI work with a robot to put that in the box?
Yeah.
So this is a demo how not so easy it is for ChatGPT to figure out. That's the question, right? So now, so what you will see now, it is looking at this screen. There's a camera on there. This robot has a RAM. It's now, I can see a green block. I can see a red block. I can see a white block, and then it will identify where it is. But now it needs to know how to pick the red block, right? So it needs to know where it is. So now red block is in the X position, Y position, Z position. The white box is there. Now you go pick it up. But now it is checked. Before I pick it up, is it safe for me to pick it up? So it's a control the gripper. Checking, did I hold it, verifying the grasp, right? And it's going through it. So it's talking to the robot continuously. Very slow, right? It's still in that process of figuring it out things. But remember, it just see everything from this camera, and then it is now, okay, where is my white box? Previously it knew where it was, but confirming where it is. And then before it moves, it is going to go and place it. Perform, move down, make sure that it's there. And again, verifying everything excellent. Robot has reached the point. Control the gripper, open the gripper, and it will put it up, right? Fine. Okay. If you want to see a slide of the camera, you can see that. This is mostly for teaching, just to understand for students, and they can test it. They have some trial programs that they can test inside it. Students, of course, they know how to do the baby versions. Right? They design that as part of the class activity. Then they can work on bigger ones if you're part of bigger classes. If you're in the research, then you can work on those. But mostly it's systems. You have to know there's mechanical, there's electrical, there's computer, there's pretty much everything that goes into a very simple sensors to put into this whole thing, right? So I think those just to give examples of how they can do it. So this is a little bit more complicated than that one, but you'll see now it has more communications, Wi-Fi.
Yeah.
So students learn just on the systems side of it and control side of it. This is one of those FANUCs. So again, if a student has a FANUC on their resume, instantly employable.
Yeah.
Because a FANUC, they probably control 65 to 70% of the world's market on industrial robots, industrial machines like these. So they are more expensive, but valuable for the skill sets that they have. So we will get a robot here, we'll get a robot also here, and then another new machine. So together we create a production cell. So students to learn, not for real reproducing something, but for students to learn on the manufacturing or the components that go into these things. So for us it is aerospace or aerospace semiconductors, a little bit of automotive. I would say these are the major industries.
Tuition or tuition, undergraduate tuition?
Undergraduate tuition, I'd say if it is out of state, it is probably around 20,000 per year. 20,000 per year. In state is around 14,000, 14 to 13,000.
And it depends on your credit course as
Depends
well.
on the credits. Depends also if you get scholarships, then they reduce all of that. 20,000 per year out of state. Again, larger robots. When these students see it, they're scared. Yes, I am also scared because that thing better not hit the pillar or the glass. We still have to install these things. But again, these are the kinds of robots that industry uses.
Yeah.
Again, FANUC, that's the competitor. We try to get students to learn or multiple, not just FANUC. Unless FANUC gives us a lot of money, but they won't. But we try to put, now these three robots have to work together. Not like that robot is going by itself, but these three will eventually get installed and they're going to do composite printing for aerospace applications.
I see.
Right? So the whole thing will be caged and then people will stand outside to see how it will operate. But again, students learn how to control this software-wise. They will have to digitally design it and virtually commission and then only put the control side. So again, controlling this is a specific type of code that you have to write for these things. And then the students will design the, this is just the arm, right? And they will design the gripper after it, right? That the professors are working with the students for new kinds of grippers to attach to that guy. This will do just drilling, painting. That will do the actual manufacturing. This will be a sight to watch because this is on a rail. They are going to install this on a rail and then this whole new robot will move back and forth.
Yeah.
Oh, wow.
So yeah, it will produce large components. Not fully installed, but I have to raise money as well. This can kill even easier because it has laser at the end. This is doing, you know the 3D printers, right? You
Yeah.
have the plastic part. Same thing.
Different material.
Same thing. It still has the same, except this is a metal wire.
Ah, I
The
see.
metal wire, metal spool, the metal will go. Next week you have the training on this one. But laser, 6 lasers will point to the part is not up there. We have the part and the part will be built. So you can do a full aerospace blade, a wing blade. This is also a robot that will turn and rotate. I hope once, maybe at some point we'll have the video of it working. But yeah, and that's why it's sort of like welding. That's why it has a special room. We have welding glass so you can see from outside, cannot be inside. And eventually we left this empty space so that another robot can paint it or
I
or polish
see.
it. So this is what we call hybrid manufacturing, right? So it's metal, so hybrid metal manufacturing. Do the 3D printing, but then also do the traditional machining. So this is what aerospace industry wants, space industry wants, defense. There's no. Do you have powder 3D printers?
Not yet.
No, okay. So there are different kinds. One is the wire kind, then you have the powder kind. Powder is what's used in medical industry, dental industry, hips, craniofacial, and aerospace. But powder is still powder. Powder gets everywhere. And metal powder is also very explosive, so you can't take that to space or any of those applications. So you have to use these kinds. But still it is in testing phase. But very little, just use the wire, go through, make the part.
Wah, ini macam.
So everything that we produce there has to be characterized and tested. So these are students learning their machines. I'm sure if you're a scanning electron microscope, optical microscope. I don't know what particular they're doing. They're doing material spectral analyzer, materials testing. Again, a lot of empty space. I hope we will add more equipment as we go. But for now, we have something so that it's done. we make them wear those, it's not very critical, but so
Mhm.
when they go to the industry, they don't like just walk in with your shorts and, you know, we're still training the students, don't come with your shorts. I know
Yeah.
it is hot. Don't come with your shorts. Still wear the lab coats when you're handling materials and gloves as necessary, just to train them. Then it becomes practice.
Yeah. Wah, bukan cuma 3 nih, banyak nih.
So in engineering, you know, many times in engineering, they don't take the first engineering class until their third year. So here we changed that a bit. In the very first semester, if you're in robotics, you will play with the baby robots.
Ah.
The baby robots first. And this you can even use in high school and all, but the assignments that we give them, they will, just like you saw downstairs, they use a camera, they use a robot, they program it, they give them assignments, like they play X and 0 game, play with the robot to do X and 0. So computer vision, like you saw the vision.
Yeah.
They know how to use it, but later on they will study how machine vision works from an algorithm math point of view. But use it in the first semester, they use it. If this program launched last year, so this is the students are in the second year now. They will practice on this. If they do it well, then they go a little bit on the yellow robot side. Again, the same yellow robots downstairs, but just maybe it's small size from Planet point of view. But you know, they learn the robot programming too. But more about maybe this one is what is better. So the robot alone is useless. Learning that is useless. You have to know the PLCs part.
Yeah.
Either Siemens PLC or Allen Bradley Rockwell Automation PLC. Together is what makes what factories need. And we teach first on how to use this, but then in their fourth year or capstone projects, you will just get a bunch of components. Here's the problem, put it together. You know, that's what engineering students need to know. Technicians, yes, how to fix this, how to repair this, how to maintain it. But engineering need to know how to design this virtually first, then write the programs for making design work. So we practice, teach that even some students learn to design new grippers for me.
Yeah.
But again, for us it is Allen Bradley PLC with the FANUC. We don't have Siemens, maybe someday. This lab can support 50 students at a time. So we have about 35, 40 on that side, but we still need more of these yellow robots. So we still have space to get rid of some of the machines. I'm not sure if you're familiar with that one. That's a 5-axis CNC machine. Same machine that you saw downstairs, but the students, they study on a more smaller scale. So they're at least used to doing that, and then eventually they go downstairs.
How many active students are we?
We have 375 students now. We just started 375. I'd say in our undergraduate, we are about 125. My hope is that we grow up to 1,000 students, 375 to 1,000 students. Because manufacturing is coming back to the US. But I need to educate and bring the high school students and parents.
Yeah.
This is a lucrative career, there is a stable career, and it's not the same manufacturing that was done 30 years ago. Lot of programming, lot of robotics, lot of automation. So, but we have to teach and educate the parents. So every Friday we have high school students come, and students just generally come and see. Oh, okay, if this is manufacturing, I can do this, right? Because many high school students have robotics clubs, but then what happens after that? They go to computer science. Like, why computer science?
Yeah.
So now, for the last 2 years, we see a drop in computer science now.
Including in our university.
So which is good. I'm good. The dean of engineering, like, what is this? How many want to get computer science? Right. So now it's oversaturated. Too many people. And now people are okay. Maybe we should look into this more hands-on and not just program all day. You can still do programming, but programming with a physical thing.
Yeah.
That I think many students naturally like that as a first preference. Computer science, 100,000 plus salary, but there is a drawback to that as well. So I think, but we have to make that case. It's not easy. In manufacturing was declining in the US. This is the largest classroom that we have. We can support up to 150 projectors everywhere. Great view. So in engineering, you know, many times in engineering, they don't take the first engineering class until their third year. So here we changed that a bit. In the very first semester, if you are at robotics, you will play with the baby robots. Baby robots first. I mean, this you can even use in high school and all that, but the assignments that we give them, they will, just like you saw downstairs, they use a camera, they use a robot, they program it, they give them assignments, like they play X and 0 game, play with the robot to do X and 0. So computer vision, like you saw the vision class. They know how to use it, but later on they will study how machine vision works from an algorithm maps point of view. But use it in the first semester, they use it. If this program launched last year, so the students are in the second year now. They will practice on this. If they do it well, then they go.
Students do a new user orientation. So that's when they come in, we give them some mandatory safety stuff about not cutting towards yourself. You have to wear safety glasses, stuff like that. And then we'll go through some building specific stuff of like how to other shops on campus will have you take a semester long course on this equipment. Which applies the helmet, the jacket, the gloves, all that stuff. We stock practice medals too. We have little coupons on the back, so if you see somebody who needs to practice,
figure out, you know, how do they know what the students are interested in? How do they shape the students to be trained in areas that's important to them? And I think so Honeywell was very interested in figuring out how they could get closer to ASU and develop their talent pipeline. And I will say now, ASU is the largest provider of interns to Honeywell. So I think this last year we had maybe 55 or 60 engineering interns. So anyway, they created this space here, and if you look at this is I wouldn't call this a hardcore makerspace. You don't see any big saws or any big machines or anything like that, but it is a makerspace. And they hold things like hackathons here. So you guys are familiar with the hackathon concept, where Honeywell will put out a problem statement on a Friday night, and students will all come in here, and this will be packed full of students. And then the students will break into teams, and then they'll solve the problem over the weekend, all day and all night. It's pretty exciting. So, but anyway, so that's one thing they do here. But across ASU is a very distributed university around the Phoenix area. So we have a West Campus, we have an East Campus. I don't know if you're going to those places.
I think they already went to Polytech.
You went to Polytech, so you already saw that. So you probably saw the spaces there. Did you go to ISTV 12?
Yes.
Yeah.
Oh, okay, so that's where my office is. Yeah. So anyway, it's so you see, the whole idea is to get students making and doing instead of just taking the regular pencil and paper curriculum, or I guess type, computer curriculum. So everybody gets a chance to be hands-on here. And so this area here We created an arrangement with Honeywell. They wanted to brand the space because they wanted all the students to see that Honeywell was a viable opportunity, a viable place to work, and maybe they weren't familiar with Honeywell. Honeywell's kind of a different company in that they make all the stuff that goes inside airplanes. They don't make the airplanes themselves, so they sometimes didn't have the brand recognition. So they thought by having with the students anyway, and so by having this place here, all tours for even new freshmen come through this space, so everybody gets to see Honeywell. And so we think this is a model of how we want to do business, with the industry. And so we're trying to do this in other places as well. So and as part of this, we do have 3D printing machines and things like that. You probably saw the same thing going at ISTV 12, but Honeywell provided that here for this place as well.
Yeah, we can do a mini tour.
Yeah, we'll walk around the space. And sometimes they actually will, like their CEO will come and have a board meeting right here in one of the rooms here. So, because that's the other thing is they want to get their leadership into the school and engage with the community. So it's worked out really well. It's been going for about 2 years now, and so we're actually about a year. A year, yeah. I mean, the planning seems like it's been going on forever, but it actually. We had our grand opening a year ago in October last year.
So there always be a regular guest lecture from the company on
Correct.
industry as well.
Yeah, and maybe Anthony can talk about how he manages what goes on in here.
Actually, just last night they had one in this space. We meet with them regularly, so we'll see how well attended it was. But overall, we advertise it amongst our aerospace engineering classes or mechanical engineering classes, depending on the topic. And then students will come and get to interact directly with industry, learn about a specific topic, and get that sort of exchange that we was looking forward to.
So is it embedded directly into the subject, or it's separate event for the student?
Separate from the class, you mean?
Yeah,
course it's separate. It's something optional that they can participate in. We just advertise within a course that might be applicable. So, like, if you want to learn more about what we're doing in class, but from an industry expert who's actually doing this regularly, here's a space where you can do that.
This makerspace. There is another makerspace that's in Poly campus that I don't know if you're going to visit that.
Actually, we were at Poly yesterday at ISTV 12.
Yeah, they do a great job over there. It's a little different. They run it differently. And then we have the Channel Innovation Center, but that's
Visited there too.
That's kind of new. That's the only problem with I love the Channel Innovation Center. It's just a little far away. I wish it was closer. So we have mostly engineering students, but we also have the School of Earth and Space Exploration students. And what we do is combine. They work together on. We'll even bring in students from management, and the business, and the finance, and the marketing, all the disciplines. So we run this more like a training aerospace company. So we bring on projects. Everything's project oriented. It's not on the semester schedule. So they'll have what you were holding was called LightCube. That launched 2 years ago. We had the last one that launched with Dora. And they do, our operations center is right here, and so we have the big screens, and the spacecraft will be on the wall, and the students will have to operate it. But the nice thing is, all the other students that are on the other projects, they see what's going on, and they have that natural, they talk and they learn. They're also held accountable for schedules and budget, which is unusual for a student kind of thing. I manage the lab. I only work half-time. There's a director that's faculty, and we are in a transition process, we'll be kind of joined under Fulton and CC. And KE, they're still arm wrestling on how that'll work out.
As
Yeah. But what it lets us do is bring in the students from all the disciplines. And we have paid students that we call them lifeguards. And it's so that they're trained on all the equipment, and then they make sure there's a level of safety, they make sure things get kept clean. And the big thing that they learn here are sort of the process. When they graduate from here, they really have about a year of experience. So when they get hired on, we have students getting hired on as team leads for software, or into more critical roles, where usually junior engineers are hired in as they don't have much that they can do because they don't have any real world experience. And they're getting the jobs at Blue Origin, Northrop Grumman, Honeywell, Rocketdyne, Rocket Lab, like all the big players. We have worked with students from France, and that was a new project last summer. The guy Lucas came for the summer, and he was on site here, and that's something that we would like to explore more. If you had students where we could trade students, and the nice thing is you learn a lot more from a student that's been working in our lab. They bring down everything that we know, and instead of we can talk on the phone, but one of the things we're doing with that French student is, since we launched spacecraft and they circle the Earth, they need ground stations that are radios with a computer that hook to the internet that talk to the spacecraft. So we're working, and we'll have a ground station in France, and then we have ours here on top of the building. I gotta say, Indonesia is a great location because it's far away.
Yes,
Yeah.
Like,
other side of the globe.
Other side of the globe,
absolutely,
like
yeah.
that would work out great. How do we get funding? We were built and initiated through, really through Michael Crow. He was working with the faculty here, Lindy, that has since gone to Berkeley, but they decided we needed a lab like this, and so they kind of fronted the money to build it. But as far as the ongoing projects, we are fortunate in that we get free rides to space from NASA, although that just ended, but we most likely will be able to get them from industry. They'll give us rides. But then we have to find the money to actually make the spacecraft. But they're not as expensive as you think they are. They're like, you could do it for $50,000 total. But now the students are doing all the labor, so there's no labor in that, but the pieces themselves. And they're very simple spacecraft. They don't have thrusters, they don't even point, they just sort of tumble. But that's okay, you can still do a lot, and the students still get a lot of sense of accomplishment to have something that actually goes this way. This is, they're building the next spacecraft that's going to launch. It'll be about the same size. Over here is all our radio equipment for talking to the spacecraft, and they do all the development. We have on the roof a rotator that will point the antenna, and we have cable trays so we can get the signal down from the roof. We have the nicer 3D printers in here. Again, that door has controlled access. It's open right now. This bench, so these benches are assigned. And so that one is assigned to Coconut, this one's assigned to Ascend. This team's building and they're a mess, I yell at them all the time, it shouldn't be this way, but they're building a payload for a balloon that'll go up to 80,000 feet. Over on the other side, there's some battery testing for the spacecraft that's launching. This was a rocket group was on the end, but it looks like it got taken over by the squid. Yeah, so this is this is actually Coconut. They're fixing the rotator on the roof. Over here we have a class. In the back we have
Is this rover?
these are rovers, yeah. We have all these little rovers, and they're building the. They'll have a GPS receiver. It has a camera on it. It's run by a Raspberry Pi and an Arduino. We have a big rover that you can sit in, like big, that this will eventually run, but they practice and they learn.
Oh, yeah.
Small. These, we have probably 6 of these, and they're great for training because they work exactly like the big rovers. And then in this, so they have soldering irons, oscilloscopes, things like that are over there. On this side, we have, this is a space simulation chamber, so this can pull a vacuum and go hot or cold. This is just a thermal chamber, can go hot and cold. And then under this box here is a vibration table that can simulate the actual vibration of launch. That requires a lot of training before we let you use it. It's an expensive piece of equipment, but once you, like Sid's trained on it, he can train other people on it. They can use it. They've used it for testing things that go to space, but also used it for research for the capsule. These other 2 are, well, this is being used for science research right now, true science research, but it's usually used for pre-launch checks. And then on this side is all our kind of mechanical. We have the mill. We have our laser printer. Our laser cutter is over here. Let's move around here. Laser cutter. The fume hood is so important because we do some painting. We do some putting stuff on. We have this tiny little CNC mill. This is great for learning how to run CNC mills, but also just small parts. And then we have our resin printer. Because it's messier, we keep it in here. We have a little clean room. And you can see they're putting, you can sneak around a little bit. They're putting the solar cells, Sid actually is putting the solar cells on the solar panels. Yeah, that's the whole of the lab, but you can see it's not that big, but we probably have 200 students through any given month. There'll be that many different. On a Friday at 5, in that room, there'll probably be 45 or 50 people. Ooh. We've had to take over another classroom close by because when 2 groups that each have.
And so there's a really cool program called the Fulton Undergraduate Research Initiative, or FURI. And so basically what that means is that the engineering school will give a stipend for students to work 5 hours a week on a project during the semester, and then they can actually work full-time over the summer through the summer undergraduate program called FURI. And so that's been something that's like, in fact, they actually have they'll work for the semester, and then they'll have a poster presentation. And that was actually yesterday. Tuesday. So you just missed it, yeah. So the cool thing though is that was like 150 students all coming together and presenting their work. And they're in like themes from data to energy to health to semiconductor manufacturing and sustainability. So like those are the 5 main themes of our school, or of the engineering school. And so it's really fun to see them get a chance to kind of share their perspective. So a lot of the work that we do is with undergrads, and they actually, I think it's super important to have undergrads get a chance to do research. And so it's fun to have that opportunity, I guess. ASU we have 30,000 engineering students, which is, I went to a pretty big university at University of Iowa, but that was more than all the undergrads in the it was more than the entire school. This is just the engineering, so that's pretty cool. But yeah, what you're seeing in our lab is a lot of the processing and characterization that we use to make low-cost semiconductor and ionic conducting materials. So we focus mostly on semiconductors like photovoltaics, or battery materials, or fuel cell materials. So a lot of energy materials are our focus. And the main way we go about producing these materials is with using inks. So like instead of you won't see any fancy like deposition chambers, you'll see things like scales that we use to weigh out powders, and you'll see coders that we use that are basically kind of like the same way they screen print t-shirts. We have different slurry coders that will basically are essentially like bars that will go over and push ink across, and then we heat the inks up, or we have spin casters as well. So very like low cost, rapid processing methods. And then we also have a spray coater as well.
And you're trying any kind of material?
We try lots of different types of materials. We can actually see opposite here. You're preparing some perovskite?
Have you tried the organic?
Okay, well he's making a polymer solution right now. But we look at, I'm just going to turn on the light real quick. Sorry not to bother you. You'll see that we have all sorts of different precursors, but everything usually starts out as a salt. So yeah, we look at it. Right now I'll be just measuring out a polymer called it's an acrylic polymer basically. But we also look at, the material that we look at most often is this, it's called a perovskite material, so it's hybrid, organic and inorganic components.
Yeah, that's why I'm asking if you have ever tried with the organic material as well, so you're doing it.
Yes, both, yes, absolutely. So the cool thing about the perovskite is it's like a class of materials. Silicon is always going to be silicon. There's only one silicon, but with perovskites, depending on how you change the atoms in the lattice, you can change all sorts of properties. And so that's like, yeah, it's shown as like this structure here. So it's like a crystalline material, but all of these different colored elements can be different, or all these different colored lattice sites can be different elements. So we can use organic material, carbon-based materials, we can use inorganic materials or mixtures thereof. And then we can get different properties. So if we want to make something that is a semi-transparent, or we want to make something that acts like a solar panel but is actually a window, so it lets all the light through, we can make a transparent solar panel. If we want to make a perovskite, these also are they're mixed ionic electronic materials. So if we want to make a battery, we can design it so that it has a lot of ions that move around. If we want to make a solar panel, we want to restrict the movement of those ions. But the cool thing is a lot of the precursors that we use are just very similar to table salt. So they'll be like different materials that you can, and it's almost like a spice cabinet, right? A semiconductor spice cabinet, because you take these materials, that's obviously has weighed out some powder there. We would add like a solvent or a liquid so that they would become dissolved or suspended, and then we can do different processing methods of that ink to create our device, and we can process these on very cheap flexible plastics, or we can put these on top of pieces of glass or silicon. I'll show you an example. And oh, by the way, this is actually a laser.
Yeah,
so we use some laser, but it's this right now. This is cutting just some masks of aluminum or stainless steel. But we also use it for patterning.
So this one included the microscope inside, right?
It has a lens inside. Yeah. And it's a UV laser. So what it does is it from Keyence actually, same company that does the microscopes. And
in Japan, right?
yes, Japanese, yeah. And so this is often used, they call it a marker, so they'll use a laser marker. So a lot of times they'll use it to make like QR, like if you're gonna create like, you want to engrave metal or something, or make a QR code or a belt buckle. I mean, that's like the commercial version, but like we're using something more for the research side, where we use it to actually create, to selectively remove and avoid layers. Because when we make, you can imagine if we want, if we want to make a large area device, we'll need to basically create individual, it's called monolithic integration. What that means is it's going to create trenches and such so that we can make many different devices on the same wafer without having to use multiple wafers themselves. So a lot of times people talk about additive manufacturing. This is, I guess, a form of like negative manufacturing. But it's actually faster because you can imagine we can coat layers down like at very rapid speeds, and our dream would be to have like a continuous production line where you're processing, putting down ink, curing it, and then removing it with something like a laser so that you can pattern and create whatever you're looking for. Whether it's like a microelectronic device or an ion conducting or a solar panel. So that's like a lot of what we do, and the other things you see around are things that we use to characterize these materials. So we have like, this simulates the lamp of the sun. So it's like having it looks like a flashlight, but it's a xenon lamp that we put down onto a probe station and allows us to check how efficiently are these operating if they were really in the sun. We actually have we work with a lot of industry partners, and we have some real panels that the industry partners make, and you can touch them. They're all protected and everything. you'll notice a few things.
You can hold like this?
Yeah, you can hold it. It's all, it's,
You hold like this.
no, however you want. It's okay, it's okay. Yeah, you can take a look too. You'll notice a couple of things. So this is a, this is from a company in the Bay Area, and you'll notice there's a couple problems. Like the edges, this is supposed to be a solar panel. So if you like hold it in the light, you'll see it should be pretty uniform, but it's starting to degrade.
Yeah.
Oh yeah.
This is the key problem that we're dealing with these materials. They're so easy to make, but they're also easy to break.
Yeah.
So like the best, it's a double-edged sword. They can be produced really rapidly, really cheaply, almost free. I mean, the materials themselves are super low cost, but then they don't last more. This is actually about a year old, and so they don't last more than a year or two. And so we're trying to come up with ways to understand how do you overcome this issue, right? Because obviously you don't want a solar panel that only lasts you
Like you have to
Yeah.
replace
every year. Yeah. And so we've been working with them to try to understand and diagnose what is the relationship between the chemical material, the properties of the chemical, the chemistry inside the panel, and also the mechanical properties. Because for instance, these it might be a little hard to see, but you can almost feel that there's a little bit of bulging because they put in, this is filled with like a plastic material, polyethylene, the same stuff water bottles are made out of, that's melted down so that it can be glued between two pieces of glass. The perovskite itself, the active layer, is trapped between that glass. It's only 1 micron thick, so that's like 100 times thinner than your hair. So very thin, right?
Wow.
And so it's protected because it's very sensitive to moisture and oxygen. But we think that by actually gluing it all together, it creates internal forces and strains that can actually drive. Because this is, the outside here is rubber, so there's no oxygen or moisture getting in through the black rubber. And so, yet nonetheless, you can see these are changing colors, they are degrading, and so we think that there are mechanical like strains that are actually leading to these actually starting to change their structure. And so
This is this part. Because you use the plastic right to become the
and that's one of the
yeah,
sorry.
and the plastic when you expose the plastic with the UV light, then it something like degrade.
So
Just like our bottle, the drinking bottle, if you put it in the sunlight for a very quite long time, then it will degrade. I guess you should do.
You're totally right. It can yellow. Excuse me. It can also create side products. So the most common plastic, I mentioned ethylene, but it's actually something called ethylene vinyl acetate. And the acetate can react and create acetic acid. Acetic acid is vinegar, and you don't want that. Will like definitely cause problems. So there's a lot of considerations that you have to keep in mind, not just the fact that there's because you can have, like you say, byproducts from the protective material itself. That's the other thing that has to be considered too. So yeah, absolutely. We're trying to understand. Actually, we have a partnership. One of our other students, Marco, is part of a partnership with the National Renewable Energy Lab. They're in Colorado, and they're trying to help. We're trying to work with them to understand what of the different plastics, why is that causing reactions? And the good news is you don't have to use that ethylene vinyl acetate. There's other plastics that could be used, but some of them are like too stiff, and so some of them can really create issues with durability, and some of them are so soft that they don't really hold together, and then they're like Play-Doh between so it's like what I love about this type of like challenge is that you can understand, you can realize that there's a lot that goes into this. This is an electrical device, but there's really important materials to be thought about. There's chemical reactions that are occurring. There's device physics that are happening, and so we have a really interdisciplinary group. Like Abhijit's actually a mechanical engineer, but he's like making stuff and characterizing and modeling their properties, right? And we have students, and if you just like look at some of the undergrads, right? So this undergrad, he was in biomedical engineering, but he started making batteries, right? Patricio is in electrical engineering. Carson's doing her PhD in Spain right now. She was in material science. And like, I think it's super important that you have lots of different perspectives because everyone sees things a little bit differently and would then point out like, oh yeah, what about, this consideration or something that you might not necessarily think about. So that's the other cool through this line, and it goes out this to this nozzle. And this nozzle vibrates. It's an ultrasonic nozzle. So it vibrates at like 20,000 times a second to create a very fine mist of particles. and then there's gas that will come down that will push that mist downwards, and it'll be like a curtain. And so actually in my PhD, I spent a lot of time developing ways to use perovskites as spray paint, basically. And so we would put perovskites through here, spray coat them, and then what it would follow behind it is what's called a plasma tool.